Welcome to Ask and Learn.
In this problem, we have let's see here. We have a bar that's kind of resting against the wall here. So we have a force normal to the wall, and then there's like a pin here, and then the bar has a force here. So it's kind of like we're wedged in here, but we know that the force at this point is going to be perpendicular to the bar. And what we're asked to determine is the distance d, basically the length of this bar, or basically the distance to this load, I guess if the bar has negligible mass. The distance here to this load for this to be in equilibrium, right? Because there's no friction against this wall. It could, if it's not the correct length, it would then just kind of rotate about this pin, and this would slide up the wall. So it's not necessarily in equilibrium unless this load is at a correct place. So we have our load here where the rod is touching the wall, and that is in the horizontal direction, and I'm going to call that the origin. The reaction force on the bar from the pin here is in, it has a magnitude F2 and is in this direction because this is theta. And we were actually given this length, the x component of the position vector. So that's just a, and then we can figure out the y component is a tangent theta. So this distance here. Then we have the applied load out here, which is in the negative vertical direction, so we have minus p. And then the position vector to that is related, it's a distance d from the origin in this direction. So we have all our forces, and we have our position vectors, and so we can sum forces and moments. And in the end, we have three unknowns in this problem. Well, actually, we're not given anything, but we have three things. We want to find everything in terms of p and a. So that gives us, and theta. So that gives us d, f2, and f1x. We want to find these three variables in terms of the rest of the parameters in the system. So we got three equations and we have three unknowns, and solving those, we get that d equals a divided by cosine cubed of theta. This is kind of an interesting relationship. I suppose you could say that as a increases, d needs to increase. So as you get farther and farther out here, then this needs to be longer and longer, which makes sense. So that's proportional. And then this cosine cubed is kind of interesting because, say if theta is 0, then this is 1, and d would have to be equal to a, which makes sense because if we have a bar like this and we have a load on it, well, we need the reaction force to be right at the load, or this bar is going to rotate because there's no other vertical force on it. So that makes sense. And if theta were we also get an infinite value when theta equals pi over 2, or so if the bar were vertical, we basically that's saying we can't keep it from sliding if the bar is vertical, because the reaction from this force and the reaction from this force would both be horizontal, and then this one is vertical, and there's nothing to react that, so we have no value of d that would work for that case. Then the reaction force at the wall is the magnitude of the applied force times tangent of theta, and then the reaction force at the pin is the magnitude of the applied force times secant of theta.